Okay, so this video follows immediately from the previous video, which was solution of simple trigonometric equations. So if you haven't watched that, can I suggest you go and start there first. In the simple equations, we had nothing going on in here inside the sine or cos function. Harder trig equations, is a very loose definition, but what I'm talking about is where there is something other than x happening in here. Okay, so in terms of solving these equations, all of the processes we looked at in solving the simple equations still apply, but we're going to need to take things a step further at the end. So what we still want to be able to think of is we essentially want to be able to think about this as the same kind of problem we were dealing with in the last question. So we've essentially got 2 times sine of something equals negative root 3. I'm just going to call that something A, okay? So this is exactly the sort of equation we were solving in the last video, simple trig equation. So the first step we want to do is make sure that we get the sine part of the function on its own. So we have sine of something equal to a number. Right, then our next step is to work out our reference angle. Okay, so sine is equal to root 3 on 2. Forget the plus minus. Okay, what's that exact value that we're looking for? So we've got sine equal to root 3 on 2. So I know that root 3 is in my half an equilateral triangle, special triangle. I want sine to be equal to root 3 over 2, which means I need root 3, to be the opposite side, and 2 to be the hypotenuse, which is obvious. So if root 3 is to be the opposite side, we must be talking about this angle down here, 60 degrees or pi on 3. Okay, so our reference angle is pi on 3. We want to think about quadrants. So we've got sine of something equals a negative value. So the y coordinate is negative, the sine value is negative. So we think about where those solutions are. Sine values, y coordinates are negative in the third and fourth quadrants. And so we're looking at pi on 3 in the third quadrant and pi on 3 in the fourth quadrant. Okay, so that is pi on 3 down from the x-axis. Okay, so once we've located the position of our solutions in the unit circle, we're then going to think about our domain. Alright, so in this instance, our domain is 0 to 2 pi. Now this is where we technically need to make some adjustment, but for now I'm just going to have a look at, okay, so if we look at from 0 anti-clockwise direction around to 2 pi, okay, so this is pi here, we're going this way, we've got two solutions. Okay, so we get pi plus pi on 3, so that's 3 pi on 3 plus 1 pi on 3, which is 4 pi on 3, and 2 pi minus pi on 3, so that is 6 pi on 3 minus 1 pi on 3, so 5 pi on 3. Again, you could count in thirds around the circle, 1 pi on 3, 2 pi on 3, 3 pi on 3, 4 pi on 3, 5 pi on 3, 6 pi on 3. Okay. Alright, so what we now know is that A, whatever's in the sine function, is equal to 4 pi on 3 or 5 pi on 3. Okay, but we're not solving this equation for A, we're solving it for x. Okay, now we essentially at the beginning here, we let A equal 2x. So let's put that back in here. Okay, so now we know that 2x is equal to 4 pi on 3 or 5 pi on 3. And so we're solving for x, which means we need to divide by 2. Dividing a fraction by 2, if you've got, I'm up at the top right here now, if you've got A divided by B and you're dividing it by 2, it's A over B times 1/2, it's A over 2B. So dividing a fraction by 2, you're doubling the denominator. So these are going to become 4 pi on 6 and 5 pi on 6. And then of course we want to make sure that we simplify our fractions, so that is 2 pi on 3. If you can do that in one step, that's fine, there's no need to write out the extra line. Okay. So I just want to have a look at, let's solve this equation with our CAS. So we had a look at this at the end of the last video. So menu 3.1 to solve as usual. We enter in our equation, 2 times sine of 2x equals negative root 3. solving for x, comma x. Now remember, we want to close off our solve function. We can't change the syntax of solve, but after here is where we want to add our restriction. So we want to solve this equation given that 0 is less than or equal to x, which is less than or equal to 2 pi. Okay, so what we find is we get 4 solutions, but we've only ended up with 2 via our solution method. So we're actually missing 2 solutions down here. And the question is, how can we adjust our process to ensure that we don't miss any solutions? And it shouldn't be a game of trial and error at the end here, just adding random solutions on until we think we've got enough. We should be able to ensure that in the process we know that we're finding all of the solutions necessary. Right, I'm going to come back to where we need to rethink this, but I just want to flick over and have a quick look at a graphing package to have a look at this situation graphically. Just let me pause the video while I open that up. Okay, so here we're looking at 2 graphs. We've got y equals sine x. I've technically drawn y equals sine of nx, but at the moment n is 1, and so we're looking at y equals sine of x. And the blue line is y equals negative root 3 on 2. Okay, apologies for the slightly difficult to read square root notation, but that is negative root 3 on 2. So remember in the past we've talked about how any equation can be thought of as the intersection of 2 lines. So we're trying to solve sine of x equals negative root 3 on 2. Okay, and so we're looking at where does the line y equals sine x intersect with the line y equals negative root 3 on 2. Now, we were looking between 0 and 2 pi. So 0 to 2 pi, we're just talking about this region here, and we found 2 solutions in that region. Here and here. They were 2 pi on 3. No, sorry, my apologies. They weren't 2 pi on 3. Let's just have a quick look back over here. So this is the solutions for A. They were 4 pi on 3 and 5 pi on 3, okay, which is what we're seeing here. So this was 4 pi on 3. Sorry, the stylus in this program isn't quite as nice. That's a 3. That's a 3. And this was 5 pi on 3. Again, that's a 3. Okay, so those were the 2 solutions we found when we were just looking at sine of A equals negative root 3 on 2. Okay, and then what we did is we said, oh, okay, but it's not A equals that, it's 2x equals that, and so we need to divide them by 2. So what I want to look at, so I've got these 2 points marked with green dots at the point of intersection. I'm just going to, sorry, the program works slightly differently here. I'm just going to erase these messy things because I think they'll get in the way when I adjust the period. Okay, so this is the solution. This diagram is showing us sine of x equal to negative root 3 on 2 between 0 and 2 pi. Now we weren't solving sine of x, we were solving sine of 2x. So let's have a think about what that does to the graph. So at the moment I'm going to adjust the value of n. So as I make n bigger, okay, we know that's a dilation from the y-axis by a factor of 1 on n. So when I make n 2, which is what we were doing, we were solving this equation. Now this is what happened in that process where we then divided our solutions by 2. So now this solution that was 4 pi on 3 became, it was 4 pi on 3. It became 2 pi on 3. Again, that's a 3. This stylus does not like to draw a 3. And this solution that was 5 pi on 3 became 5 pi on 6. Okay, so those 2 solutions are still correct, but the problem is we are looking for all solutions between 0 and 2 pi, and we've now got 2 additional solutions in this domain. So let's think about where they came from in that process. Okay, so if we put n back to being 1, okay, they were actually these 2 solutions over here. Those 2 solutions, by the time we then dilated the graph by a factor of 1/2 from the y-axis, i.e. by the time we changed from sine x to sine 2x, those two solutions came to be within the required domain, 0 to 2 pi. So actually, when we were solving that initial equation, sine of ax equals negative root 3 on 2, we needed to find all the solutions from 0 to 4 pi. So that then, once we squashed it all in, once we then considered sine of 2x equals root 3 on 2, which is a dilation by half, we actually had all the final solutions. Okay, so that's a little untidy. Let's go back to our notes file over here. Okay, and let's think about what happened. So actually, the issue was that here, at this line, when we were getting our initial solutions here, we found all the solutions from 0 to 2 pi, but actually, we should have found the solutions where a was between 0 and 4 pi. Okay, and then that would have meant that by the time we got down here, x would have been between 0 and 2 pi. Okay, and that's because, remember, a is equal to 2x. Okay, so what we're essentially saying here, sorry, I know this is getting a little untidy, what we're really saying here is we want these solutions here to be between 0 and 4 pi. 0 and 4 pi, okay? Now remember, a is actually equal to 2x. And so that means that we want 2x to be between 0 and 4 pi, which when we divide that inequality by 2, which will certainly give us x between 0 and 2 pi. So what we actually need to do is to make an adjustment to our domain. Okay, so we need to think about, actually we need to do 2 laps of the circle initially. So we need another 2 solutions here. So we need 3 pi plus pi on 3, so that's 10 pi on 3. And we need 4 pi minus pi on 3. So 4 pi is 12 pi on 3 minus pi on 3, so that's 11 pi on 3. So we needed those 2 solutions there. So that then, when we're saying 2x is equal to that, then we divide everything by 2, and so we get 10 pi on 6 and 11 pi on 6, and then we just simplify the fraction there, that's 5 pi on 3 and 11 pi on 6. We now have solutions that match what we got in the cas. So we need to do this domain adjustment, and I've made a bit of a mess here, but let's have a think about what that means in the next example, just to see. So we make that adjustment, that 4th step. So first step, we're getting sine or cos on its own. Second step, we're identifying using our exact values, what's the reference angle. Third step, we're thinking about which quadrant, where in the unit circle are our solutions. Then we're using our domain, and it's at that 4th domain step here that we're going to need to think about, well, if I need x to be between 0 and 2 pi, what does that mean for 2x? Because I'm actually solving for 2x at this step. Okay, so let's think about that extra step in this example. Okay, so I won't need to go and look at graphs and things. That's just to give us a sense of why we're getting those extra 2 solutions come into the domain when we do that, add in that dilation. Okay, so step 1, we want to get cos on its own. So we're going to have root 2 cos of 3x equals negative 1. Now I'm not going to introduce a here, you shouldn't need to do that, okay? But that was the point, was just that we're essentially initially ignoring what's happening inside the cosine function. We're just focusing on what we did before, and then we'll worry about that at the last steps. Okay, so we've got cos of something equals negative 1 on root 2. So exact values, again, I know the minute it's got root 2 involved in it, it has to be about pi on 4, okay? So my reference angle is pi on 4. Cos is negative, alright? So cos being the x coordinate, we're looking at where in the unit circle. Actually, I'm just going to make that circle a little smaller. Give me some room to go around it. A bit too small. Okay, so we're looking at cos being negative, so 2nd and 3rd quadrant, and pi on 4. So we're looking at here and here in our unit circle. So pi on 4 up from the x-axis in there, and pi on 4 down from the x-axis in there. Okay, so what we've got to remember now is that the solutions that we're going to get out of the unit circle, they are equal to whatever is inside the sine or cos function. So at this next line, we're going to have 3x is equal to, and that's the solutions that come out of my unit circle. Solutions that come out of here are going to go there. Okay. So then what we will do in those next steps is we will divide all those solutions by 3 to get our values for x. Okay, so what I want to do is I want to think about, what do I know about my domain? So I know the final domain at the end, down here, x has to be between 0 and 2 pi. So I know that I need x to be between 0 and 2 pi at this final line. The previous line, we're not solving for x, we're solving for 3x. So if x has to be between 0 and 2 pi, what does 3x have to be between? 0 times 3 and 2 pi times 3. So at this line, out of the unit circle, we need our solutions to be between 0 and 6 pi, so that then when we divide them all by 3 in that last step, they will be between 0 and 2 pi. Okay. Alright, so 0 and 6 pi is 3 laps of the circle. Okay, so we're going to go around once and get our first two solutions. We're then going to go around again and get our next two solutions. So we're now at 4 pi, and we're going to go around a third time and get our final two solutions, so that we're then at 6 pi. Okay. Alright, so this was the first lap, so that's pi there. Second lap here, that's 3 pi there. Third lap here, that's 5 pi there. Okay. Alright, let's work our way around. So the first solution is at pi minus pi on 4. Okay. So that is going to be, I'm just going to write them straight in over here. That's going to be 3 pi on 4. My next solution is at pi plus pi on 4. So 4 pi on 4 plus 1 pi on 4, that's 5 pi on 4. My next solution, all the way around again, is 3 pi minus pi on 4. Okay, so that is 12 pi on 4 minus pi on 4, so that's going to be 11 pi on 4. And 3 pi plus pi on 4, so that's going to be 13 pi on 4. Round again, we're looking at 5 pi minus pi on 4. So 5 pi is 20 pi on 4 minus pi on 4, so that will be 19 pi on 4. And 5 pi plus pi on 4 will be 21 pi on 4. Okay, so there's my 6 solutions out of the unit circle that I found by going from 0 to 6 pi, so doing 3 4 laps of the circle. Right, now 3x is equal to all of these values. We need to solve for x, so we're going to divide everything by 3. Dividing everything by 3 will mean my denominators become 12, 3 pi on 12, so that will simplify. If you want to simplify that as you go, by all means do that. 5 pi on 12, 11 pi on 12, 13 pi on 12, 19 pi on 12, and 21 pi on 12. Alright, then we want to make sure our final answers are simplified. That's pi on 4, 5 pi on 12 is simplified, 11 pi on 12 is okay, 13 pi on 12 is okay, 19 pi on 12 is okay, 21 pi on 12 will be 7 pi on 4. Okay, you can simplify those fractions as you go. So there's our final set of answers. Okay, so that little step of adjusting your domain. Okay, so this bit over here on the left, work out if you want x to be between something and something, what does that mean for what you're actually solving for at this previous line. Okay, let's look at another example. Alright, so this time we don't have a dilation factor, we've got a translation, but the same logic applies. We need to be careful about what domain we're looking for the solutions in, so that then when we do that last step, we have solutions that are where we want them to be. Okay, so process is still the same. Get the sine or the cos on its own. It is on its own. So we've got sine of x plus pi on 3 equal to 1/2. Okay, so sine equals 1/2. Again, thinking about our exact values, half the equilateral triangle. If sine is 1/2, we want the 1 to be the opposite, and so that means we're looking at pi on 6, or 30 degrees up here. So my reference angle is pi on 6. Sine is positive, so we are in the first and second quadrants, the top two quadrants where the y values are positive. Pi on 6, and out this way, pi on 6. Okay, so at the next step, our answer is going to be x plus pi on 3 equals however many solutions we're going to get out of the unit circle. Then at the next step, we'll solve for x, which means we will subtract pi on 3 from all our solutions. Okay. Alright, so we need, at this final step, we need x to be between 0 and 2 pi. That's the domain for that final line. So we need to work out what does that mean for this line where we're not actually solving for x, we have solutions for x plus pi on 3. So we're adding pi on 3 if we're going in that direction. When we're solving, we'll go the other way, so we're subtracting. But we're working our way backwards for now to work out what does it mean for the domain. So we've added pi on 3 to x, so we need to add pi on 3 to 0, and we need to add pi on 3 to 2 pi. Now you could just leave that as 2 pi plus pi on 3 if you want, but that's going to be 7 pi on 3. Okay, so in my unit circle, I need to go from pi, find all the solutions between pi on 3 and 7 pi on 3. Okay, so what you need to, what's worth noting here is that this is still a single lap of the circle. Okay, we haven't actually, there's no dilation here, it's just translation. So the distance from pi on 3 to 7 pi on 3, oh, sorry. The distance from pi on 3 to 7 pi on 3 from there to there, that's just 2 pi still. So it's just one lap of the circle, but it's not starting at 0. Okay, it's starting at pi on 3. And that's important here because in my unit circle, here's pi on 3, here. So we want to do one lap of the unit circle from this point, pi on 3, around to this point, 7 pi on 3. Still one lap of the unit circle, we're starting somewhere different. Now that makes it, that's important because actually what we see here, if we're not doing a lap from 0 to 2 pi, pi on 6 isn't a solution. Okay, we're not interested in pi on 6, we're interested in this solution here, which is pi minus pi on 6, and we're interested in this solution around here, which in this domain is 2 pi plus pi on 6. So the two solutions we want here are pi minus pi on 6, that's 5 pi on 6, and 2 pi plus pi on 6, which is 13 pi on 6. Okay, we're not interested in pi on 6. I'm going to write the pi on 6 solution in there because the temptation is not to make this adjustment. I'm just going to put it in there, just put it in a, I'll just put it in a, oh sorry, I'll just put it in a grey pencil here. If we added pi on 6 here, okay, at this next step what we're going to do is we're going to be subtracting pi on 3 from all of our solutions. So to go from this line to this line, we need to now minus pi on 3. So we need to do that to everything. Okay, so we're subtracting pi on 3 from all our solutions. So thinking about the fact that pi on 3 is 2 pi on 6, okay, common denominator so we can subtract fractions, pi on 6 minus 2 pi on 6, that would be negative pi on 6, which isn't in the domain, which is why we don't need that solution. Okay, subtracting 2 pi on 6 here is 3 pi on 6, and subtracting 2 pi on 6 here is 11 pi on 6. Making sure we simplify any fractions, so that is pi on 2 and 11 pi on 6. So two solutions, but it's important that you adjust the domain initially so that you find the right solutions out of the unit circle so you don't end up with solutions you don't need. If you hadn't done that adjustment, you would have had pi on 6 and 5 pi on 6 as your first two solutions. You would have then subtracted pi on 3 and found you had negative pi on 6 and 3 pi on 6, and then you would have needed to go back and find an extra solution. Okay? But this is a way of being really, or check that there aren't any more solutions anyway. This is a way of being really sure that you're finding the right solutions at the outset. Okay, let's do one more, a bit complicated. We've got the translation and the dilation happening here, but process is the same. So let's stick with that. So the first thing, actually we've got another extra complication here as well. The first thing is to get the cos on its own, which it is. You can expand that bracket in there if you want, but you really don't need to. It doesn't do anything different. Okay, this time we're thinking about our exact value. When does cos equal 0? Okay, and this is where people get tied up in the special triangles, you know, pi on 3, pi on 4, pi on 6. But we know when cos equals 0. Cos is the x-coordinate. The x-coordinates are 0 at pi on 2 and at 3 pi on 2. Okay, so we're talking about up and down here. Alright, so drawing in my unit circle, a little rough sketch, but I should have drawn it bigger. So we're actually interested in the solutions happening in these locations. That's where cos equals 0. Right, we need to think about our domain. So there's going to be two steps here. Well, I think it's easier to think of it in two steps. What's going to happen is whatever we get out of the unit circle is going to be equal to whatever expression we've got inside the cosine function. So that is 3 times x minus pi on 4. It's going to be our solutions out of the unit circle. Then, after we've got those solutions out of the unit circle, we'll focus on solving for x, which means we will divide all those solutions by pi on 3. Divide them by pi on 3. Divide them by 3, so we'll end up with x minus pi on 4 equals a whole lot of solutions, okay? And then we'll add pi on 4, and we'll get x equals our final set of solutions. Again, let's think about domain. So we know here, at this final line, we want x to be between 0 and 2 pi. So that means that x minus pi on 4 is going to be between negative pi on 4 and 2 pi minus pi on 4. So that's 7 pi on 4. Which means that this line, which is 3 times that, is going to be between minus 3 pi on 4 and 21 pi on 4. Okay. So out of the unit circle, we want to find all of the solutions that are between negative 3 pi on 4. So that's around here. Negative 3 pi on 4, okay? And then we want to work our way around the circle until 21 pi on 4. Now you can just count if you want. This is negative 2 pi on 4, negative 1 pi on 4, 0. Okay? Pi on 4, 2 pi on 4, 3 pi on 4, 4 pi on 4, 5 pi on 4, 6 pi on 4, 7 pi on 4, 8 pi on 4, which is 2 pi. 9 pi on 4, 10 pi on 4, 11 pi on 4, 12 pi on 4, 13 pi on 4, 14 pi on 4, 15 pi on 4, 16 pi on 4, which is 4 pi, 17 pi on 4, 18 pi on 4, 19 pi on 4, 20 pi on 4, 21 pi on 4. Okay. So it's still 3 full laps of the circle, okay? This 3 here, this dilation of 3, and we've seen that in previous examples, is essentially going to tell you you need to do 3 laps of the circle, okay? But we don't want to do it starting at 0, or we won't have the right solutions, okay? So we've started around here at negative 3 pi on 4, okay? And then we've travelled all the way around, so this was 0 here, this is pi here, this is 2 pi, therefore this is 3 pi, this is 4 pi, therefore this is 5 pi. Okay, so thinking about our solutions here, so remember they're located on the y-axis here. So this first solution is actually a negative solution. It's between 0 and negative 3 pi on 4. That's negative pi on 2. The second solution around here is positive pi on 2. The third solution is at positive 3 pi on 2. Around here. Around again, this one's going to be 5 pi on 2. Around again, this is going to be 7 pi on 2. And around again, this one's going to be 9 pi on 2. Okay, sorry, I've got us a bit crowded here. Let me see if I can just move my unit circle out of the way a bit. Okay, so now we've got our solutions out of the unit circle. Now we focus on solving for x. This is just a linear equation. You've got 3 times x minus pi on 4 equals a number. Okay, so we're first going to divide by 3. Okay, I'm going to go back to my black pen. We now want to divide all these solutions by 3. Okay, which means the denominators will all become 6. Now, I wouldn't do any fraction simplifying here. It's easier to keep them all with the same denominator to do the subtraction at the next step and then worry about simplifying at the end. Okay, so we've now got minus pi on 6, pi on 6, 3 pi on 6, which will simplify, but it's not our final solution, so let's not worry about that right now. 5 pi on 6, 7 pi on 6, 9 pi on 6, which will also simplify. Right, then, those solutions are all equal to x minus pi on 4, so we now need to add pi on 4 to all our solutions. Okay. Now I'm going to take an extra step here to get a common denominator. Okay, so actually what I'm going to do here is I'm going to add in an extra line here, which is going to be my common denominator here is 12. So this is minus 3 pi on 12, and I know this seems a bit tedious, but it's worth it in the long run to save you time. So I'll just move that next line down a little. Okay, so I'm going to write them all on 12ths. So this is minus 2 pi on 12, 2 pi on 12, 6 pi on 12, 10 pi on 12. Now you might be able to do that common denominator in your head as you go with each of them, but you've got quite a lot of numbers going on here, so I would say sometimes it's worth just investing some time. Okay, so now we are adding 4 pi, which is adding 3 pi on 12 to all our solutions to get our final solutions for x. So adding 3 pi on 12, this solution now becomes 1 pi on 12, this becomes 5 pi on 12, this becomes 9 pi on 12, which will simplify. I'll do that at the same time. 9 pi on 12 will be 3 pi on 4. This one will become 13 pi on 12. This will be 17 pi on 12. And this will be 21 pi on 12, which again will simplify. We've got that common factor of 3, so that will be 7 pi on 4. And there is our final set of solutions. So I know it looks a bit messy, and it is a bit messy. These are harder trig equations, okay? But adjusting your domain for whatever's in the sine or cosine function, and then needing to perform those steps at the end to get x on its own. Okay, have a go at the questions on the worksheet.